We weren't able to have our meeting this morning due to some computer issues, but I wanted to show you a thing here. What I've got is a light box. It's basically just a light bulb in a box that shoots light out of different slots. And so you can see here as I put my hand in the way, it's just light hitting my hand in more or less parallel lines. Now what I'm going to do is I'm going to take a concave mirror and I'm going to put it on here, and you're going to see how placing this mirror on here causes it to reflect the light. Now, you'll notice that these light rays that are coming in parallel lines are being bounced and refocused to this point right here. Okay, that would be the focal point. So if I take a piece of paper here, and I'm going to mark a point where I've got the mirror. I'll turn the lights on in a minute so you can see this a little bit better. I'm going to place the mirror on that point at that distance. Then I'm going to mark the focal point F right there. I'm going to turn the light on for just a minute. Ah, it's so bright. I'm blind. Okay. And so you can see, there's the position of the mirror. There's the focal point. Oh, let me see if you can still see it here. Yeah, very cool. So this distance from here to here, that is distance F. Now, if we were to measure that in centimeters, that's inches. Nerd. Okay. I'm getting about maybe 2.3 centimeters. So F equals 2.3 cm. Now, if I wanted to find R, which is the distance on this mirror from this point to the center of its curvature, if we were to take this thing and extend that into an entire circle, R, the distance R would be the radius, then it would be F times 2. So then R here would be 4.6 centimeters. Anyway, I wanted to show you that. A couple other things I'm going to show you. I'm going to turn the lights back out. So putting our concave mirror back on there. Now, if I flip this around and turn it into a convex mirror, I want you to see what happens to all of these lines. Okay, you see how instead of being focused, they're being reflected away. One is being reflected directly back. This one's being reflected away there. This is being reflected there. If I were to plot all of those lines, and let me just do that real quick. Get this lined up right. Okay. If I were to plot all of these lines, let's say that one is coming out this way, one is coming out this way, and this way. Okay. And of course, the one that's being directed or reflected directly back there. I'm going to turn the lights on one more time. Sorry about that. Okay, we'll wait for it to adjust itself. Okay, so this right here would be more or less where the mirror was sitting. If I take these lines that I've got drawn here and I extend them backward, this is not perfect. Do you see how they seem to converge right here? Well, then that right there is still going to be the focal distance of this mirror. Now, any image that you would see in the outer curved part of this convex mirror would be a virtual image, okay? It's going to, what you're actually seeing is not going to be light rays that are coming back together like we had with the concave. You're going to be seeing a virtual image. So it's going to appear right side up, but it's going to be reversed left to right like you typically see when you look into a plane mirror, say in the bathroom. Now let me take a measurement of that. I have a feeling it's going to be awfully close to what we had a minute ago. Okay? And again, if I go from where the edge of the mirror was to the center of this, it's right about 2.2 or 2.3 centimeters. So the focal distance, if you've got a concave, convex mirror like this, concave on the inside, convex on the outside, the focal distance, F, is determined by the curvature of that mirror. It doesn't matter if you're coming at it from this direction or from this direction back here. Let's look at something else. Because in addition to some mirrors, I've got some lenses here. So let me kill the lights. I'm going to take this first lens, which is a little skinny, and I'm going to place it in the path of these light rays, and I want you to see what happens. You take a look, what's happening here is it's passing through here, and all of them are being reflected more or less toward this point right here, okay? So this right here is the focal point of this lens. Now, we're going to get into the math very, very soon. In fact, I think I'll record a video about that. I'll try and give you the heads up on when that will be, if you want to take part in that. But the math behind lenses and mirrors, if you're talking thin lenses and curved mirrors, is identical. And so you can still, the distance from the lens to the focal point is F. You can still look at magnification rates. One thing that's interesting, if you notice, this up here, this first ray, let me see if I can color that using one of these little color paddles. This first ray up here, I'm going to make it green. Notice how it's being bent, and then it's being, as it's being refracted, it's going down toward the bottom end here. If I do a couple of them like that, or three, actually just flip the paddle around here. There's like the first three. Notice that they're being shot to the opposite end of things. And so a image that's going to come through here is going to be inverted. If this was the top, then these light rays as they are refracted through here end up at the bottom on the other side of things. The lens in your eye does this. And so as the lens in your eye gathers light from the outside, the image that's projected into the back of your eyeball is actually upside down. It's inverted. Your brain takes it and flips it back over to make it right side up. So that's probably way more information than you really wanted to know. I'll go ahead and wind this video up. Have any questions or comments, please feel free to post them here or post them back on Google Class, and we'll talk more about it. See y'all soon.